This is session 4, Jesus and the Fine-Tuning of the Universe. Last week, we introduced the concept of arguments for the existence of God, which we engage in when we do natural theology. And we define natural theology as the branch of theology that has to do with presenting evidence for the existence of God without appealing to sacred scripture or church authority of any sort. And we said that we do this because God has given to us two books which give us information about him. There's the book of Scripture, inspired writings mediated through the Holy Spirit. And then there is the book of nature, from which we get the word natural theology. We're not talking about natural theology distinguished from unnatural theology. Rather, nature is the book that God has given to us through which we may infer certain things about him, his existence, his nature, his qualities, and so on and so forth. Now, there are at least two purposes of natural theology. One is natural theology bolsters the faith of believers. Personally, I have been deeply enriched by my study of natural theology because it strengthens my faith. It helps me to be assured that I have a reasonable basis for my faith. And then also, natural theology helps us build bridges to non-believers, helping them to I guess connect the dots in perhaps arriving at an understanding or a knowledge or an appreciation of the possibility or even the probability of the existence of God. And so it's very useful for that. Um, we also talked about the fact that in modern contemporary society, science is somehow thought to undermine belief in God. Yet, as we read in Stephen Meyer's article last week, he wrote that modern science has stopped backing atheists and started pointing to God, stopped backing atheists and started pointing back to God. And he says that the weight of scientific evidence strongly supports the argument for the existence of God as creator of the universe. And so this is an exciting time to be doing natural theology. Now, to back up even a little bit broader in our perspective, we're doing this because we're trying to understand what Paul perhaps is talking about in a fuller way when he describes Jesus as the agent of creation in the Colossian Christ hymn. He says that Jesus is the cause, is the originator of the universe. And we're seeing that natural theology adds weight to that biblical statement. For example, we looked at the Kalam cosmological argument. Now, the Kalam cosmological argument is an ancient argument. It was developed very early in the history of the church and was taken up in the latter part of the first millennium by a Muslim theologian, Al-Ghazali, and he did a lot of good work with this and provided philosophical backing for the argument. And then Dr. William Lane Craig, the eminent Christian apologist, a philosopher, theologian, wrote a doctoral dissertation in the 1970s on the Kalam cosmological argument and revived it and has really launched it into being one of the most hotly debated and investigated arguments for the existence of God. And the word Kalam actually is interesting in that it's a tribute to Al-Ghazali that Craig did by linking it to him, because Kalam is an Arabic word that means word or discourse or even perhaps theology. So here is the Kalam argument. You remember it's a deductive argument, which means it has premises and a conclusion. Now, a deductive argument can be a very powerful argument because if you write premises, make assertions which can be proved or demonstrated to be more plausibly true than false, then the conclusion is irresistible. It's inescapable. If the premises are more plausibly true than false, so then the conclusion is true. So here's premise number one. Everything that begins to exist has a cause. And we're going to pause here because I think that this is a very good time to attack this objection that sometimes we hear from non-believers or atheists. And they say, well, so you're claiming that God created the universe. Okay, well, then who created God? Okay, that's a tough one, but it's really not a tough one because the question is incoherent. By definition, metaphysically speaking, God must be uncaused because he's the greatest possible being that could exist. He is uncreated. He has no cause. He is eternal. He would have to be God. If he weren't, then there must be a greater being than him, a superior being than him. Or if you don't say that it has to stop with this God, then you have the challenge of saying, well, if then well, okay, who created God? Well, then who created God? Well, whoever created God has to be greater than God. Well, who created the greater God and the greater God and the greater God? And you have this endless regression. You just kick the can down the road, so to speak. So for those who say who created God, it's a ridiculous question that betrays a total lack of understanding of this. So premise one, everything that begins to exist has a cause. Premise two, the universe began to exist. Therefore, the universe has a cause, and that cause must be God. Now, the final step, that cause must be God, is understanding God in this broad sense, the maximally great being, the greatest conceivable being. He, or that entity, must be God. And from there, we can then begin to do some conceptual analysis and say, okay, well, if the God, if God is the first cause, the uncaused cause, or the prime mover, well, then what properties must he have? Well, as we said, he must be immaterial, he must be transcendental, he must be a mind, he must be eternal, and so on and so forth. He has to be all of those things, or he would cease to be God or couldn't qualify for the position. He is God and God alone. And then we concluded with our link between all of what we've said and Paul's description of Jesus as being this cause, as being this God, this one identified as the one through whom all creation came into existence. And as we said, it was created for his glory and his honor and his praise. So today we're going to continue with another scientific evidence for the existence of God, and it's taken from the field of contemporary astrophysics and cosmology. It's the breathtaking development of the understanding of the fine-tuning of the universe for intelligent life. Over the last 75 years, scientists have discovered that there's remarkable evidence of the fact, yes, the fact, this is really not in dispute. Scientists across the spectrum all accept the fine-tuning of the universe. The universe displays remarkable qualities and evidences of being cosmically fine-tuned. Now, before we go on, it's important to understand that the term fine-tuning is a neutral description. That is to say, it's not a term used by theistic philosophers or scientists. No, it's used by all scientists, theists, non-theists, and so forth. And so it doesn't prejudice the issue towards a theistic or non-theistic interpretation. Scientists all agree that the universe has been fine-tuned for intelligent life. So it begs the question, so what is fine-tuning? Well, that's what we're going to talk about today. So we're going to start with the document, and this contains a definition by William Lane Craig, and I think you'll find it's a pretty good one. So what is fine-tuning? Scientists have been stunned to discover that the physical constants and arbitrary quantities in the universe have values that fall within an astonishingly narrow life-permitting range. So that small, short definition contains a lot. We've got constants, and we've got quantities, and we've got ranges, and we've got life permitting abilities in the universe to support life and so forth. So we're going to unpack it all. So don't worry about it. But what we're really saying here is that this fact that the universe is fine-tuned seems to suggest or strongly implies that the universe has been designed for life. Now, I'm going to get you to pause the video now and watch the video clip by William Lane Craig called "Cosmic Fine Tuning." And I think that you'll find it challenging. Perhaps some of the material may be new to you. Some of it perhaps you've heard. But I want you to focus on just getting the gist, the big idea, the main focus of the video. And then when we return, we'll start to talk about it a little bit. So go ahead and watch the video now. Okay, let's have a closer look. Fine-tuning exists in three categories. Now, this is in your notes, but I've got it on the screen here for you. Fine-tuning is observed in three categories: the fine-tuning of the physical laws of nature, the fine-tuning of the constants of physics, and the fine-tuning of the initial conditions of the universe at the time of the Big Bang. So remember those three categories: the laws, the constants, and the initial conditions. So what does all of this mean? Well, in order to really understand this, we need to have a refresher on what's involved in the Big Bang. So we'll put up a Big Bang timeline for you here. And here we have the history of the universe. Wow, what a topic. So if you start over here on this end, you see what is the Big Bang. Written as this explosion, so to speak, at t equals 0. And this is called the radius of the visible universe. So we know that the universe began with the Big Bang. It's followed by what are called quantum fluctuations. And then the next stage is called inflation. And then it follows through to where we are about 13.8 billion years later as the universe continues to unfold and expand. So let's look at this timeline. But before we go into it, I think it might be really, really helpful to talk about a common misconception. I just use the word explosion, and I don't like the word explosion because the word explosion conjures up this image of some chaotic, destructive, random event where a building blows up, or a car blows up, or an airplane blows up, God forbid. But it's kind of like when something blows up. In our experience, it blows up in a building or a city or something like that, and the explosion blows up and destroys everything, and it blows up into something else, and we may be hit by the fragments or the debris or so on and so forth. That's not the kind of explosion we're talking about. The Big Bang is not that kind of explosion. It's much better understood as a fine-tuned expansion event. A fine-tuned expansion event. You see, before the Big Bang, there was no time, there was no space, there was no energy, there was no matter, there was nothing. And cosmologists say that the Big Bang started with the singularity. So if we go to the far right of this timeline and go back to the very beginning, to the 0, when there was nothing, this infinitesimally small point is called the singularity. It's a place of almost infinite density and heat. The universe at that stage, at t equals 0, time equals 0, was very, 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 very dense and very, 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 very hot, unimaginably so. And so it's really important that we understand that this event was like the unfolding of the universe, and it happened in just a very small amount of time. This fine-tuning aspect that we're going to be talking about is called the initial conditions. This is what happened in the first second of the universe. And the universe at that stage had what was called low entropy. Now, the word entropy, again, can be a confusing word, and I'm no scientist, but I've tried to understand this. Entropy means If it's low, it means it's highly organized. The condition is highly organized. Physicists talk about, a closed system, where you have energy, okay? And if it's closed and nothing can enter from the outside, then you have what we call increasing entropy. It seems to be, according to the second law of thermodynamics, that all systems like that eventually run down. They lose energy. They lose organization. The atoms stop hitting one another and it just dies, and then it reaches a point of equilibrium where there's no energy left. And that's a place of high entropy. So high entropy means low organization. Low entropy means high organization. So what was the state at t equals 0? It was low entropy. In other words, it was highly organized, a beautifully, perfectly balanced distribution of mass and energy. You remember in last week's session, we saw in the video the wind-up doll to illustrate the second law of thermodynamics. You have a wind-up doll, and you turn the key, and you turn the key tight, and then you let it go, and then the wind-up doll starts to work, and it does its thing, and it'll do that as long as there's what? Potential energy being converted into kinetic energy, right? The little wind-up puppy is moving, and but the longer it moves, the more the energy is depleted, and then pretty soon it reaches a point of what? High entropy. It won't do anything anymore. And in fact, that's what's happening to the universe. This initial energy that was built in the universe almost 14 billion years later is still driving the universe. It's usable energy. But cosmologists tell us that the energy of the universe will eventually be all used up. Now, the good news is it's not going to happen this weekend. It's going to happen a long time from now. But the universe is dying. And physicists call this the heat death of the universe. At some point, this wind-up doll, which is the cosmos, will stop moving, and we will have a dead, lifeless, dark, cold husk of a cosmos. That is the apocalyptic end of the universe. And it's because this energy that was built into the system is all being used up. Let's go through the timeline and just point out how incredible the initial conditions were for the Big Bang. So we've dealt with this common misconception. Now at t minus 43, that is, slice a second up into that very, very, very trillionth of a trillionth of a trillionth of a trillionth of a trillionth, and on and on, and a temperature of a billion degrees. All of this mass and energy, all that the universe will ever contain, is in this infinitesimally small point beyond which there was nothing. And then we talked about this rapid expansion. It's called inflation. At t 10 to the negative 23rd, the universe suddenly had a massive burst of inflation or expansion. And remember, the universe doesn't expand into space. Space is created in the Big Bang. So we shouldn't think of the universe expanding into space. No, as the universe unfolds, space is created with us. In fact, I thought of this illustration that as we're meeting today, we're planet surfing. Planet Earth is being carried along with the rest of the universe on a wave outward. We're at the center of this Big Bang, and we are being carried farther and farther apart from everything else. The universe continues to expand. And this is one of the great discoveries, really a mind-boggling, earth-shattering discovery of the last century. So we have this expansion. And look at this. In 1/1,000,000th of a second, all the physical forces of the universe are present in 1/1,000,000th of a second. At 1 second, now we're at the inflation. At 1 second, one snap of the finger, the cosmos has expanded or inflated to 20 light years across. That's 117.6 trillion miles in the blink of an eye, snap of a finger, the universe has grown. At 3 minutes, a mere 3 minutes in, all the basic elements are present. 200 million years later, wow, there's a long period of nothingness. No, no, no. During that period, the stars and the galaxies are being formed. 9 billion years after the Big Bang, our sun is formed. 9.5 billion years, Earth is formed. 10 billion years, life first appears on Earth. And so I think you get the big idea here about the Big Bang. Now, one of the great physicists who has helped us understand this is a guy called Roger Penrose. And Roger Penrose has written about the fine-tuning of the initial conditions of the universe, which we've just talked a little bit about. And you asked the question, okay, so the initial conditions were fine-tuned. How precisely did they have to be fine-tuned for the universe to exist and for life to exist? Well, Roger Penrose, leading theoretical physicist, cosmologist, here he is. Roger Penrose, a renowned Oxford scientist, recipient of the 2020 Nobel Prize in Physics, writes, how big the original phase volume, that's that singularity we're talking about, that volume, that space, that area, that region, how big the original phase volume that the creator had to aim for must have been precise to an accuracy of 1 part in 10 to the 10 times 123. He continues, even if we were to write a 0, so imagine taking a Sharpie and going throughout the universe and writing a number on each proton of every atom and each neutron of every atom in the entire universe, and then also on the subatomic particles. Yeah, let's put a number on all of them. So you take your Sharpie and apply a number. If we could do that, we would still fall far short of writing down the number needed to express the precision required to set the universe on its course. Pretty incredible. So fine-tuning of the initial conditions. We also said that fine-tuning involved the constants. So let's describe and discuss the contents a little bit. Refer to your notes now. Find where it asks the question, what are constants? Now, probably the word constant is somewhat familiar to you. You may remember it from high school math, physics, and so forth. Well, constants are numbers or values that, when plugged into the laws of physics, determine the basic structure of the universe. So a constant is a value or a number that is inserted into the laws of physics. So when the laws of nature or physics, and we can say the laws of physics include gravity, electromagnetism, the strong nuclear force, the weak nuclear force, and there are other things here which we don't need to get into, and I frankly don't understand. But you know, the basic laws of nature that govern the functioning of our universe and structure of our universe, when those constants are plugged in there, you have the kind of universe that is created by the laws. And so let me give you an example of a constant. You all recognize this guy, Albert Einstein. Well, he wrote this very famous equation, E equals mc squared. You remember that one from science class? Energy equals mass times the speed of light squared. I think most of us know that one. Good. Give yourself a pat on the back. Well, here's probably not as well known, but equally important, I would think. How many of you know this one? Well, it's the equation for a Big Mac. Big Mac equals 2 beef patties, special sauce, pickles, lettuce, onions, and cheese, all packed into a sesame seed bun. And notice on this document, I've written, okay, watermarked confidential. E equal mc squared is not confidential, but if you disclose the Big Mac formula, you may suffer physical, emotional, and spiritual trauma. So just be careful. Consider yourself warned. So back to your class notes, because there are some blanks which I want you to fill in. Let's flesh this out a little bit more. So when inserted into the physical laws, these constants determine the basic structure of the universe. Constants are not determined by the laws of nature. Second, these constants are independent of the laws of nature, which is saying the same thing twice. But the implication is this, that the laws of nature could operate on a different set of constants, in which case we would have a very different universe. The universe could have been very different than it is. Next point, all these constants and quantities fall into an extraordinarily narrow range of life-permitting values. And that's the point. Earth could be different, the universe could be different, but life would not be possible if that were the case. If these constants and quantities had been altered by even a hair's breadth, and you remember the dial in the video that you just watched, incomprehensible, one tick of the dial, a hair's breadth, life-permitting balance. We live in a life-permitting universe, not a life-prohibiting universe. Why? That's the big question. But if those constants were altered, life would be destroyed, would not exist. And then the final point, without fine-tuning, there would be no stars, no galaxies, or planets. There would be no atoms, no molecules, or elements. There would be no chemistry. Wow. So now we see that the initial conditions are fine-tuned, the constants and arbitrary quantities of the universe are fine-tuned. We're talking about considerable fine-tuning. So here's a multiple choice question before we go on. How many fine-tuning parameters are there? So they talk about parameters in the scientific literature. What are parameters? Well, think of parameters as, boundaries or limits put on a range of some sort. For example, you can't go out on this end of the range, you can't go out on that end of the range. And here we're talking about the parameters are so narrow that the margin of error is almost zero. It has to be perfect in order to operate. So how many of these finely tuned parameters are there? One illustration that occurred to me would be something like, from life would be something like golfing. Okay, I hate golfing because I'm no good at it and I don't have the patience to try and improve. It seems that it's just a devil-inspired sport. Anyway, I was thinking, if you were to talk to a golf pro, somebody knows what they're doing, and say, hey, okay, 300 yards down there, there's a green, and there's a hole, there's a flag, you can see it from here. Tee a ball up, take your golf ball, tee it up, and here's what we're going to do. If you can put the golf ball in the cup, we are going to give you $1 million and a new car. Whoa, the pro says. Whoa, that's a challenge. Okay, that's I don't know if I can do that in one stroke, but maybe two. Yeah, I think I could do it in two. If I get a good drive, I'll do it in two. Three for sure, but I'm willing to give it a try. So he gets up there, he gives that ball a mighty whack, and boom, it goes, and it's heading right. It bounces at the lip of the fringe of the green and rolls up towards the stick. And I mean, he's got his hands up, and with bated breath, he watches as the ball approaches the cup and just touches the cup and squirts off to the right. Missed it. So anyway, well, nice try. We've got some consolation prizes for you. We're gonna send you to McDonald's for a Big Mac. Yeah, maybe the fries and drink we'll throw in. So the pro walks up to the cup and he says, "Man, just missed it by that much." And he looks, and to his amazement, the cup is not the standard size. The cup is the size of the golf ball. And he says, well, that's cheating. That's not fair. This was impossible. The parameters are wrong. Oh, parameters are wrong. I mean, you have to have a bigger cup than the ball. And the organizers say, no, just take the ball and put it in the cup, place it in the cup. And sure enough, there is a millimeter left over, and the cup will accept the ball. That's the concept of parameters, the range. Well, how many of these parameters of physics, of fine tuning, have been discovered? Is it A, 16, 45, 112, or 150? The answer is 150 so far. That's a lot of parameters. So parameter upon parameter upon parameter, it just increases the unlikelihood that this could happen by chance. It strongly, strongly suggests that there's an element of design. Let's talk about another constant. So this is another very interesting one. This is called the cosmological constant. So here is a bit of background. Einstein shook the world with his theory of general relativity. And in doing the field equations, he found that the math didn't quite work out. Einstein believed, as everybody believed at that point, that the universe was static, unchanging. It was not growing, it was not shrinking, it was just there, always had been, always will be. It was eternally the same. And when he started to do his field equations, he found out the math didn't work out and it was just slightly off. And so he said, okay, well, I mean, it's impossible. According to the math, the universe is expanding. That can't be right. We have to make it neutral. It can't change. And so he inserted in his equation what is called the cosmological constant. Now, you talk about a fine-tuned parameter. Look at this. 1 part in 10 to the 120. So I've written all the zeros out so you can see how incomprehensibly small this is. Look at that. Now, that's an itsy bitsy teeny weeny piece of fudge. Oh, what does that mean? Well, Einstein fudged the equation to keep the universe static. He inserted that because it contradicted his concept of the universe, which was wrong. And only after some other physicists accepted the fact that the universe was expanding did the empirical evidence come in that in fact demonstrated that the universe was in fact expanding. And it has been said that Einstein said that the cosmological constant was his biggest blunder as a physicist. There's some question as to whether he really said that, but it's been attributed to him anyway. And strangely enough, cosmologists now insert the cosmological constant because in fact the universe is expanding and it's being driven by this mysterious constant, and so it's all quite a mystery. But that shows you how precise the this constant is. Another illustration that I read, which illustrates it is this: if you were to stand at one edge of the universe with a rifle and aim for the other side, your task would be to shoot a bullet and hit a single proton of a single atom on the other side of the universe. You would need that degree of accuracy, okay, to correspond to the accuracy of the cosmological constant. So I think you get the big picture. Well, I think we'll call it a day. Hopefully that you have enjoyed this and it's been helpful to you. Make sure that you have that video handy for you, because we're going to watch it a second time through. You'll be looking for something different. Second part will focus on the explanations, the possible explanations for the fine-tuning of the universe. And so we'll see you back here for part 2. Thank you.